In a previous lesson, we saw that pumps convert the mechanical energy of a turning shaft into hydraulic energy in the form of pressure and flow. This pressure and flow can be converted into linear mechanical force by cylinders which apply force in a straight line to extend or retract a cylinder rod. In this lesson, we will see how pressure and flow are converted into rotary mechanical force by hydraulic motors. We will also see how the efficiency of motors can be changed so the force they develop can match the work being done as closely as possible. Three types of motors are commonly used in industrial hydraulic systems: the vane motor, the gear motor, and the piston motor. While each of these motors looks similar to its counterpart pump, each operates on a principle exactly opposite of the pump. That is, hydraulic motors take fluid under pressure, apply it to the surface area of an internal moving part to create a rotary force, and then return the fluid to tank. When operating any motor, two main factors must be considered: torque and speed. Torque is the rotary force applied to the shaft, usually expressed in pound-inches. Speed is the rate at which the shaft turns, usually expressed in revolutions per minute. Let's look at a vane motor to see how pressure and flow in a hydraulic system affect the motor's torque and speed. Like the vane pump, the vane motor has a rotating group with vanes that ride along an offset cam ring. Fluid moves in and out of the motor through port plates. As system pressure rises, the force applied to the vane increases, and the rotary force developed at the shaft, the torque, also increases. As long as the size of the motor remains the same, increasing the pressure will increase the torque. If pressure drops, torque drops. A similar relationship exists between flow rate and speed. If flow through the motor increases, then the vanes will turn faster, and the speed of the shaft will increase. Again, this direct relationship between flow rate and speed is the same for all hydraulic motors. Increasing the flow rate will increase the speed, and decreasing the flow will decrease the speed, as long as the size of the motor remains the same. The size of a motor means its displacement, or how much fluid it can hold. In a vane-type motor, changing the displacement can only be done by changing the cartridge assembly, which is the rotating group and the cam ring sandwiched between the port plates. Increasing the size of the cartridge assembly without changing the pressure will increase the torque, because the vanes of the larger cartridge assembly have more area exposed to pressure. Decreasing the size of the cartridge assembly without changing the pressure will decrease the torque, because the vanes in the smaller assembly will have less area exposed to pressure. Increasing the displacement without changing the flow rate will slow the motor down, because the same amount of fluid has to fill a larger space inside the motor. And decreasing the displacement without changing the flow rate will speed the motor up, because the same amount of fluid only has to fill a smaller space inside the motor. Now, let's take a close look at how each type of motor works. In a vane motor, the motor won't turn until there is a seal between the vane and the cam ring. That means that centrifugal force cannot be used to force the vanes out to the cam ring at startup. In some vane motors, springs are used to hold the vane against the cam ring. This can be done with a coil spring or with a spring attached to a post. In either case, once the motor is turning, fluid pressure is directed to the underside of the vane to help maintain a tight seal. Fluid pressure may also be used to force the vane out before the motor starts. This is done by using a check valve, which prevents fluid from entering the motor inlet until pressure is high enough to force the vane out against the cam ring. Gear-type hydraulic motors operate in a way that is similar to vane-type motors, except pressure at the motor inlet pushes against the sides of the gear teeth, forcing them to rotate. A tight seal between the gears and the housing minimizes fluid leakage past the teeth. The torque created at the motor shaft depends on the pressure at the motor inlet and on the exposed tooth area. The greater the pressure, the greater the torque, and the more exposed tooth area, the greater the torque. The movement of the gears in the gerotor motor is similar to the gerotor pump. Pressurized fluid enters the port plate, pushing on one side of one tooth of both the inner and the outer gear. Since fluid on the outlet side is allowed to exit through the outlet port, there is very little pressure to oppose the gear movement, and both gears rotate. The torque developed is based on how much pressure there is at the inlet port and on the size of the gears. The higher the fluid pressure, the greater the torque at the motor shaft, and the larger the teeth, the greater the displacement and the greater the torque. In a piston motor, fluid pressure pushes against the pistons. The piston shoes are forced to slide up and around the swash plate, turning the cylinder barrel as they move. After each piston passes the top of the swash plate, it starts back down, forcing fluid out of the piston bore and through the outlet port as the shoe and piston ride back down the swash plate. Increasing the pressure forces the piston shoes more firmly against the swash plate, increasing the torque applied to the cylinder barrel and to the shaft. Unlike vane motors and gear motors, piston motors can be reversed without changing the direction of flow through the motor. This type of motor is called an over-center piston motor because all that's needed to reverse the direction of rotation of the shaft is to tilt the swash plate past or over its center. As the swash plate is tilted toward vertical, the motor displaces less and less fluid. Usually, to reverse direction, the motor is stopped. When the motor is restarted with the swash plate tilted over center, the piston shoes, which had been rotating in one direction, go back the other way, turning the cylinder barrel in the opposite direction and reversing the direction of the motor shaft. Both speed control and torque control of hydraulic motors is common in industry. Usually, speed is controlled by flow control valves, while torque is controlled by varying the pressure or the displacement. Let's look at speed control first. Generally, flow control valves are used in three kinds of circuits: bleed off, meter in, and meter out. Bleed off circuits do not provide accurate speed control for motors because they do not really control flow into or out of the motor. Instead, they only control the flow to tank. As a result, any leakage from the system or leakage from the motor remains uncontrolled and will affect the speed of the motor. Meter-in circuits do not work well for similar reasons. For example, the valve in this circuit reduces the motor inlet pressure from 1500 psi to 850 psi. If leakage from the motor is 3/4 of a gallon per minute, then the speed of the motor will be based on 7 1/4 gallons per minute. Now, if the load pressure on the motor increases to 1250 psi, the valve will maintain the same flow rate into the motor, that is 8 gallons per minute. However, since pressure inside the motor will be higher, leakage will be greater, perhaps as high as 1 gallon per minute. As a result, only 7 gallons per minute pass through the motor, and it will slow down. However, flow control valves in meter-out circuits control the flow that actually goes through the motor. Installing the valve just downstream of the motor will control the motor speed regardless of variations in pressure or leakage. We learned earlier that changes in inlet pressure can affect the torque a motor produces. Torque can also be affected by changes in outlet pressure and by changes in load. Changes in outlet pressure occur in all industrial systems because there is always some back pressure present in the tank line. Usually, back pressure is at least 50 psi, and frequently it's as much as 100 psi or more. In this system, 100 psi back pressure prevents the motor from moving the load because back pressure attempts to turn the motor in the opposite direction. 800 psi less 100 psi back pressure leaves only 700 psi available for a load which requires 750 psi to move. Actually, even 50 psi of back pressure could prevent the load from turning. This is because the torque required to get a load turning, the breakaway torque as it's called, is usually greater than the torque required to keep a load turning, the running torque. Industrial motors are rated for both breakaway and running torque, as well as a third kind of torque, starting torque. Starting torque is the amount of torque the motor can actually develop to get a load turning. When torque must be regulated at different speeds, a variable displacement piston motor can be used. Increasing the angle of the swash plate increases the displacement and the torque, while decreasing the angle decreases the displacement and the torque. In addition to regulating the speed and the torque of motors, it is often necessary to slow down a motor and its load. Sometimes a motor is simply allowed to coast to a stop, and sometimes mechanical brakes are used. But hydraulic motors can also be dynamically braked as well. This means that the power of the motor is used to stop itself. A brake valve can automatically apply just enough back pressure to keep a load from running away with the motor, but still allow the motor to develop its full torque. Braking can also be achieved on demand by using a directional control valve and a standard relief valve. To brake the motor, the directional control valve is shifted to its center position. This blocks flow out of the motor and applies back pressure that slows the motor down. The setting on the relief valve determines the maximum back pressure which will develop. When back pressure reaches that setting, the relief valve opens and back pressure drops off. Bidirectional motors, motors that can rotate in either direction, can be braked in a similar way. In this circuit, for example, the same relief valve can be used even though the motor can be braked in either direction. The dual check valves isolate the braking side of the circuit no matter which direction the motor is turning. For example, the check valve on the left prevents fluid from returning to the left side of the circuit when the motor is braked while turning clockwise. And the check valve on the right prevents fluid from returning to the right side of the circuit when the motor is braked while turning counterclockwise. When two different loads must be braked, two relief valves may be used to apply two different braking pressures in the same circuit. In this circuit, for example, one valve limits braking pressure as the motor turns in one direction, and the other valve in the other direction. Changing the valve settings changes the braking pressure. Whenever hydraulic motors are braked, some method must be used to make sure fluid is available at the motor inlet. If this is not done, the motor will cavitate and may be damaged, just like the pumps we saw earlier. Three methods are generally used to ensure that the motor is continually supplied with fluid. One method uses a directional control valve in which the center condition connects the motor's inlet to tank. For example, when the valve in this circuit is centered, back pressure brakes the motor and fluid flows from the tank, preventing cavitation. Another common method uses make-up checks. These are very low pressure check valves which allow fluid to flow out of the tank and into the motor. The last method uses crossover relief valves. In this circuit, one or the other of these two relief valves discharges fluid to the motor inlet, depending on which way the motor is turning. Make-up checks are still required in the circuit, however, since some fluid will be lost through the motor drain and across the directional control valve. Control of the torque and the speed of hydraulic motors also permits control of horsepower. That's because torque and speed determine the work a motor can do in a given amount of time, its horsepower. As we learned in an earlier lesson, output horsepower is equal to torque times speed divided by the constant 63025. When motors and pumps are combined with each other in systems, it is possible to control torque, speed, and horsepower. If both the motor and the pump are constant displacement, these systems are usually referred to as hydrostatic drives. If either component has a variable displacement, the system is sometimes called a hydrostatic transmission. Hydrostatic drives and hydrostatic transmissions can be either open loop or closed loop, depending on how they are configured. An open loop system has the motor inlet connected to the pump outlet and the motor outlet connected to tank. In a closed loop, however, the motor outlet is connected back to the pump inlet. This forms the closed loop. Any fluid leakage in a closed loop is made up by a replenishing pump. Since most of the fluid in closed-loop drives and transmissions is carried in the system piping, only a small reservoir is required. This allows closed-loop drives and transmissions to be very compact. The speed, torque, and horsepower of hydrostatic drives and transmissions can be either fixed or variable, depending on the type of pump and motor used. If a constant displacement pump and a fixed displacement motor are used, the system can deliver only a fixed speed, torque, and horsepower. Systems using a variable displacement pump and variable displacement motor provide the most flexibility. They are able to produce variable speed, variable torque, and variable horsepower. Two other hydrostatic transmissions are common. One uses a constant displacement pump and a variable displacement motor. Since the pump produces all the power available to the system, the horsepower is fixed, but the speed and torque can be varied by the motor. The other transmission uses a variable displacement pump and a fixed displacement motor and produces variable horsepower, variable speed, and constant torque. In most industrial systems, the prime mover of hydraulic motors is usually another motor, an electric motor. In fact, in many applications,